Hello everyone. In this lecture, we are going to discuss some pipe flow problems in different situations, and we are going to use the formula that we have derived in the previous lecture, that is the Darcy-Weisbach equation. So let's start with a very simple example where we have two tanks like this, and from the tank having a higher water level, water will flow to another tank which has a lower water level. Let's say this higher water level is 5 meter, and this water level is measured from the top of the water surface till the center line of the pipe, that is the pipe entrance. Now in the second tank, let's say for example the water level is again 2 meter. Now this 2 meter is again measured in this tank from this water surface up to the center of the entry to the or the exit point of the pipe or entry into this second tank. So that's how these heads are measured. Now the formula that we have derived was FLV square divided by 2GD, which equals the head loss due to friction in this pipe. That means total head loss in this pipe will be a function of velocity, then length, and a friction factor F, and this diameter of the pipe. Now this length, let's say it is 10 meters for this example. Now we also know that while entering this pipe at the entry point, there will be some loss. This loss is because, let's say this is the tank, here you have all the water. Then as water enters this pipe, it will not enter smoothly. Very near this entry, water will start flowing in this direction, and as soon as it enters this entry cross section, it will converge a little bit, and then it will fill up the whole pipe. Because of this transition, there will be some turbulence in this region, because this part will have low pressure and high pressure at this point will push the water back, and therefore some kind of turbulence will be taking place, and in that turbulence some extra amount of head will be lost. So that's what this entry loss means. Now this entry loss or head loss due to entry is also given as a function of the velocity inside this pipe, that is the velocity head v square by 2g is multiplied with some coefficient k. So this k will depend on how smooth the transition is. That is, if you take this example where there is a sharp transition between the tank and the pipe, then generally the value of k is approximately 0.5. Now if you want to make a difficult entry, that means if you insert the pipe here a little bit into the tank, then water will have to flow like this. Then some more head will be lost, and therefore it will increase up to 0.7 or 0.8 and so on. Another way of increasing this coefficient or increasing the head loss is if you restrict this entrance. Then water will flow like this, and some more turbulence will take place here before the entire pipe is filled. We can reduce this head loss by making this transition easier or smooth. That can be done by this kind of a transition where this entry into the pipe from the tank will be very smooth and very minimum head will be lost. In that case, this value of K will be either 0.4, and it can theoretically it can go to 0. It means no head loss, but some head will always be lost, a small amount. So it can go maybe 0.05 and so on. So for this example, we are simply going to take K as 0.5, which is the case for ordinary plumbing. So that is the first head loss while entering the pipe. Then some extra head will be lost while flowing through this pipe. That will be given by this formula, which we have derived earlier. Then as soon as the water exits the pipeline and enters this tank, we have already discussed in the previous lecture that this velocity head, whatever it had, it would be v square by 2g. We are never going to recover that head. That head will be lost because this will cause some turbulence, interstatic water here, and that turbulence will after some time die down, and by viscous dissipation that movement will be lost and the energy will be spread or leaked to the surroundings in form of heat, vibration, sound, etc. So we have now 3 types of head loss in this single problem. Now the total head loss in this case can be directly found out because we know the water levels in both the tanks. That means while water is coming from this tank and reaching this tank, here the total head is 2 meter, and in this tank the total head was 5 meter. That means we have lost 3 meter of head. Now this 3 meter of head is lost by a combination of loss at entry, loss due to friction in the pipe, and loss at the exit. So that's how we are going to make our formula or the equation for solution. Now this is a function of velocity. This loss will also be a function of velocity, and loss at entry will also be a function of velocity. One thing here, this velocity head loss or the loss at exit is equal to v square by 2g, and there will be no coefficient multiplied with it, and that's because no matter what kind of arrangement you make at this point, either it is smooth transition or abrupt transition, that whatever was the velocity will always be lost. We can never recover them, and that's why this value of K is always equal to 1. So now let's formulate our problem. We have this 2 meter water level here and 5 meter water level here. This has to be up to the center line of this tank and also center line of this exit point. Now we know that the total head loss, let's call it delta H or whatever name you want to give, is equal to 3 meter. Now this delta H, we know it is the summation of entry loss or HE, let's call it HEN, plus friction loss HF, which will be given by Darcy Weisbach equation, and plus the exit loss, which is v square by 2g, let's call it HEX. Now all these strings together will be equal to 3 meter. Now let's write their formulas one by one. K into v square by 2g plus FL v square by 2g d plus v square by 2g, that is equal to 3 meter. Now the only unknown thing here is V. The length is 10 meter, and D for this problem, let's say it is 0.025 meter, which is 2.5 centimeter, or approximately equal to 1 inch. 1 inch is actually equal to 2.54 centimeter, and generally commercial available pipes are in inches in the market. So it will be either 1 inch pipe, half-inch pipe, quarter-inch pipe, and so on. So just to keep some common ground with that, let's call it 0.25 meter, that is 2.5 centimeter, approximately 1 inch. So now another thing remaining is F, and that F is the friction factor, which will be representative of the frictional properties in the pipe. Now that can be found from the Moody's diagram, and the Moody's diagram, if you remember, it was a chart like this where lots of curves were drawn like this, and we know that beyond a certain Reynolds number, in this axis we had Reynolds number, in this axis we had the value of F, and these different curves were for different kinds of relative roughness. So in this case, we'll look at the Moody's diagram later on in some other problem, but for this case, let's say the friction factor is approximately 0.03. So what we can simply do is now put all these values. So K is 0.5, then V square by 2G plus 0.03 into 10 meter into V square divided by 2G into 0.025 plus again V square by 2G is equal to 3 meter. Here the only unknown remaining is now V in all these equations. G we already know, it is 9.8, and from this you can find out whatever is the value of V. And once you find out the value of V, you can also find out what was the actual discharge. It is, let's call it Q. Q will be equal to velocity into cross-sectional area. This cross-sectional area we can easily find out, it is just the cross-sectional area of the pipe, that is pi into d square by 4. So you can solve it and find out V and Q. Now let's take another example. Here the pipe was not long enough, so therefore we had to make a joint here using some kind of socket. So let's take the same numbers here, 2 meter, then 5 meter. This length is from here to here, let's call it 4 meter, and from here to here it is 6 meter. So in this case, again the head loss is, let's say delta H is equal to again 5 meter, but now since this joint is there, some more head loss may be possible. That's because let's say you have a pipe like this and another pipe like this. I'm just drawing the longitudinal sections of the pipe, and these pipes are now joined by another socket, and so there will be this kind of irregularities here where some extra turbulence will be taking place, and because of that also some more head will be lost. So what we can do is, in this case the total head loss will be same, 3 meter. So the formula will be slightly different. That means we'll use head loss at entry plus head loss in this section, this segment of the pipe, which is F, let's call it L1, which is 4 meter, then V square by 2GD plus, because of this joint, whatever loss is happening, that is again expressed as another as a function of velocity again. That will be K, that's some coefficient Kj into V square by 2G plus F into L2 V square by 2G D plus the exit loss, which is HEX, should be equal to 3 meter. Now these two can be joined together because the diameter is same in this case, and therefore we can take all the other things common and use L1 plus L3, take the sum and club them to only one term, that is FLV square by 2GD. But we cannot do it if these diameters were different. In this example, we are taking the diameters as same, and therefore we can, instead of writing two terms, we can simply use one term using the total length L. Now, again, this coefficient will also depend on the type of joint. That means if you join these two pipes, suppose you weld them together, suppose this is the longitudinal section of the pipe, and in between you make a welded joint and then machine the inner part and make it very smooth. The outside doesn't matter. So if the inside is very smooth, then this coefficient of loss in joint will be very close to 0. That means we can ignore this term. But if it is not so smooth, that means if you join with a socket, threaded socket, in that case the turbulence will be here and it will be having some positive value, let's say 0.5 or 0.6 for this example. So this way again we can find out by putting all these known values. Again we can find out the velocity of flow inside this pipe, and then we can also find out the discharge just by multiplying the velocity with the cross-sectional area. Now let's take another example here. So in this case, at some point we have enlarged this diameter of the pipe at this point. So let's call this L1, it may be 2 or 3 meter, then L2 and L3. These two diameters are same, this one and this one, but this diameter is different. So in this case, if we try to use a similar approach, then delta H, again let's say it is 3 meter when this is 5 meter and this is 2 meter. Now this delta H will be given by head loss at entry plus frictional head loss inside this length of the pipe, that is F L1 Phi1 square divided by 2G D1 plus head loss because of this joint, so that will be given as kj into v1 square by 2g, then plus head loss over this length, which will be fl2 v1 square by 2g d1. Then at this point, because of this abrupt transition, again some head will be lost because of the turbulence created. Let's say this is the first pipe and suddenly the diameter increased. So for some part of the flow, this part will be having a high velocity, but this part will be having a low velocity. And again at this point, the velocity will decrease because the cross-sectional area has increased. And from our knowledge of Bernoulli's equation, we know that when velocity decreases at this bigger cross section, velocity will decrease because of bigger area. If velocity decreases, pressure increases from our knowledge of the Bernoulli's equation. If pressure decreases, if pressure increases, but at this point we know that pressure was less and velocity was more. At this point, pressure is more but velocity is less. That means at this point the flow will be confused, because here it has high velocity and low pressure, and here it has low velocity and high pressure. And therefore in this region, which has low pressure, but the velocity is also not that much, because most of the fast flow is concentrated at the center, and towards the side that velocity is not transferred yet. And therefore, because this portion has high pressure and this portion has low pressure, so water will come back to this corners. And because of that, while flow is taking place like this, some flow will come back and cause this kind of turbulence. And because of that, some extra head will be lost. Otherwise, that whatever velocity is the water is having or the fluid is having while flowing in these kind of turbulent eddies, that velocity could have been used in actually flowing in this direction, but now that energy is lost just in moving around in these kind of turbulent eddies, and that energy will be lost again by the same principles, by creating sound, then heat, vibration, etc. If you make this transition smoother, that means instead of an abrupt increase like this, if you make it like this, then that turbulence will not be there. The streamlines of the flow can very smoothly diverge and fill up the bigger section of the pipe. So in that case, the loss will be less, and now we are going to express that loss again in terms of the velocity, that is let's say k k dash, which is velocity, which is the coefficient of loss in sudden expansion. So into v2 square by 2g, that is, it is expressed as a function of velocity in the second pipe, not in the first pipe. And so this loss is there. Then some extra loss will be in this length of the flow, that is again you are adding f L2. Now it is v2 square, remember, because in this pipe the velocity will be different because the discharge is same, but the cross-sectional area has now changed, it has increased, and therefore we cannot write a single v. Therefore we have written v1 in the previous terms, and now we are writing v2 and divided by 2g d2, and finally whatever was the velocity at exit, which will be v2, because that if you convert to head, velocity head, it is unrecoverable and it will be again the loss at the exit, which is v2 square by twice 2g. Now this whole thing will be equal to 3 meter, and that's how we are going to solve the equation. But now the problem is we have one equation and the unknowns are 2, that is d1 and d2 are actually not unknowns. We know the diameters. L1, L2 and L3 are also not unknowns. Again, we know their lengths, and these coefficients of loss at entry, joint, expansion and exit, they are also known based on some chart or something. But still we have v1 and v2. So using one equation we cannot solve using one equation we cannot solve for two variables. So therefore we need to make them one variable, and the very simple trick for that is, instead of writing v, we can write them as in terms of discharge, because the discharge through this pipe is equal to the discharge through this pipe. That means whatever amount of water is flowing through this pipe, the same amount of water is also flowing through this pipe, because they are just connected in series. Only difference will be the velocity. Here the velocity will be more, and here the velocity will be less. And therefore, instead of writing this equation in terms of v1 and v2, what we can do is we can express them as in terms of discharge. So this v1 will be discharge divided by area of the first pipe, that is A1. That means in place of v1 we are going to write q by A1. It was squared, v square, so q by A1 square. Similarly here also q by A1 square. Similarly here. But wherever we found v2, instead of v2, now we are going to write q by A2 squared, and here also q by A2 whole squared. Similarly here. So now we have one equation and only one unknown. This is equal to 3 meter. So by solving this equation you can find q directly, and you can also find out the velocities in this pipe and also this pipe by dividing by their respective areas. So that's how we are going to solve this kind of a problem. Now let's take another problem. It's simpler, but only difference is, instead of a tank on the other end, it's simply discharging into the open or the atmosphere. So in that case, what we are going to do is we'll take the head difference between this exit point, that's the center of the outlet of the pipe, and the water surface. Let's say this is 5 meter now, and so the in this case what will be the head loss? Now the head loss will be this total 5 meter, because after entering this pipe it will lose some head here, some additional head while flowing through this pipe, and at the end it will have this velocity, but that velocity will again be lost into the atmosphere because now we are not storing it anywhere. So therefore the equation will be simply H at entry, head loss at entry plus head loss at the pipe, inside the pipe over the entire length L, and head loss at exit is equal to 5 meter, and head loss at entry is K, which is the coefficient of loss at this point, at the entry point, into V square by 2G, and head loss at exit is simply V square by 2G. No coefficient is needed, it is 1. So this is how we are going to solve this kind of a problem. I'm not going to solve the values. You can put any numerical value and keep and find out the solution, the numerical answer. Now let's take another example. Here, instead of leaving a horizontal pipe here, now we have bent the pipe upwards. Now at this level, the water will be released to the atmosphere. That means now the head difference or the head loss will be this level and its difference from the original level. Now let's say this is 3.5 meter. You can take any other value. This is only for the example. So in this case, again, there will be some loss here. So that is H at entry plus loss at this pipe, which will be given by FLV square. Let's call it L1 because there are two pipe segments. FL1 V1 square by 2G D1. Now, since the pipe has bent here, there will be some additional loss due to the bend. Now, for that again, we have a similar formula which will be given by K at bend. This is a coefficient multiplied by V square by 2G D. For simplicity, let's not write this subscript 1 here. That means this diameter and this diameter are the same. Therefore, the velocity will be same. So this is the loss at this point, and then additional loss will be while flowing through this pipe segment, that is plus F L1 should be here, then FL2 V square by 2G D, and plus finally the head loss due to exit, which is V square by 2G. Now this will be equal to 3.5 meter. Now again, solving this, you can find out what is the velocity. Now in this case, we have introduced another type of loss, which is KB. This again will depend on how sharp this bend is. If it is bent like this or this, whatever direction you choose, then a sharp bend will cause more turbulence because water was originally flowing this way, then it will not very smoothly transition to this direction, and there will be some turbulence here, and because of again that turbulence, some extra head will be lost, which will be represented by this term KB into V square by 2. Here D should not be here, it's only 2G. Sorry. So this is how we are going to incorporate for loss in this bend. If the bend is made very smooth like this, then value of this KB will decrease. If the bend is very sharp, then the value of KB will increase. And the actual value is generally available in different kinds of charts. and in many cases some manufacturers who make these kind of joints will also provide you this kind of chart. So again we can find out the value of V by solving this equation. Now let's go to another example. It will be similar example, but the only thing is this is an expansion and you have to take care of two velocities, V1 and V2 at these two pipes, and therefore since you cannot solve this directly, you can express this as Q by A1 and this as Q by A2. Since A1 and A2 are simply pi d1 square by 4 and pi d2 square by 4, therefore these are not exactly unknowns. The only unknown here remaining will be Q, and you can find out Q by solving the equation. Now in this example we are going to see whatever was the velocity after you solve for it. Because of this velocity, how high do you think the water will flow? It has a velocity head v square by 2g, and if you convert that to head, then you'll get some value, but this value will not be exactly equal to this much. And that's because whatever velocity head was remaining at the end of this pipe, that will not be equal to this much, because some head will already be lost while flowing from here to here. So you can do that using any kind of practical if you hold a pipe like this, which is coming from a tank or an overhead tank, and turn it upwards, then water will only flow to a small height, only suppose this much. But you can raise it up to a higher height by blocking the pipe at the exit. That means if you block half of the pipe, then water will flow a little bit higher. Then if you block even more of the pipe, then water will flow through a very narrow stream, but it will even flow even higher. So why is that happening? And that's because if you are blocking this pipe, you are affecting the whole flow, and the entire velocity inside this pipe will be decreasing. And therefore the head, since we have found from the whole equations that the head loss is a function of velocity. As velocity increases, head loss increases. But if you decrease the velocity inside the pipe, the head loss will also be decreased. Once you block this pipe, maybe using your finger or maybe by closing a valve here and so on, so that way you are actually decreasing the velocity inside this pipe and therefore decreasing the head loss. What does it mean to decrease the head loss now? That means at this, inside the whole pipe, earlier we have seen that the pressure at this point was more than pressure at this point, or reversely, pressure at this point is much less than pressure at this point. Now if you have reduced the velocity, pressure at this point will not be reduced that much, it will be much higher. And similarly, pressure at this point will also be remaining very high, because water is flowing very slowly, and therefore there is a small amount of loss only, and whatever pressure was here, almost at this point, only a small portion of that pressure is actually reduced and most of the pressure is still intact at this point. Therefore, once you release it through a very small opening, then that entire pressure head will be converted to velocity head and it will flow very high up to theoretically this level, but some friction will be there, always there. Therefore, it will not exactly reach here. Some height will be left. And if you again open it, suppose halfway, and then again the velocity will increase, and as velocity increases, the pressure also decreases, and that means at this point less pressure will be available to push the water upwards. If you completely again open it, then it will only flow up to this much height. Now let's take another example. So this is a very household example. Suppose you have an overhead tank. In this tank, let's say you have water up to, from this level, the water level at this point is suppose 10 meter, and you have your tap at 1 meter height. Now from here up the top of the water surface up to the opening or the outlet of the tap, the head loss is now equal to 9 meter. Now this 9 meter head loss will be again the summation of head losses at different points. That means as water enters here the pipe, the head loss will be loss at entry. Then over this length of pipe, let's call it HF1 to the first length. Then at this bend, then HB1, say some head will be lost. Then over this length, some additional head will be lost, HF2. Again there is a bend, HB2. Then friction loss over this length of pipe, HF3, and so on. Then again here is a bend plus HB3, another length. Now this length we are going to consider up to the tap. That means the point where the tap actually blocks the water, can block the water. So up to that length we are going to consider the fourth line pipe segment, that is, and the head loss due to that will be HF4, suppose. Now in this case, at the valve or at the tap, it's a it is controllable. Now if it is completely open, there may, if it is not very properly designed, then there will be some loss. So let's account for that loss by calling it H. We can call it head loss at the tap or a head loss at the valve. So that loss will be there. Then after that, this small segment of pipe is still there, or you can, if it's very small, you can simply call it just a head loss at the bend if you don't want to account for this small length. Just the bend will be sufficient. HB, what number of bend is this? HB4. And finally head loss at exit. Now you see, so many things have to be added just to find out the accurate velocity through this pipe, and this should be equal to 9 meter. Now all these other types of head losses we have discussed: head loss due to friction, bends, entry, exit. One thing we have not discussed is head loss at this valve. Now it is actually similar to what we were doing in this case by blocking this using our finger. So that was acting as a valve. So what we were doing using our finger was, if we were blocking more of the pipe outlet, then we were decreasing the velocity, and that would have to be accounted in the equation, but we were not very structured about it. So let's now consider this example. Here this hv will again be a function of the velocity, and it will be again given as some k. So that k is, let's call it kv multiplied by v square by 2g. So this will be the head loss due to this valve. Now if this valve is completely open, then this kv value will be some small value, let's say 0.2. If it's a properly designed valve where while it is completely opened, the pipeline becomes very smooth, there is no obstruction. Once you close it halfway, then this value will increase. Then it may go to, suppose, 2 or 3. Let's call it 3. Once you close it 2/3 or 3/4, suppose, that means only small amount of water is allowed to flow through this tap. So in that case, this coefficient increases up to, for example, let's say 20. Now here, this is a control mechanism, or this is used to control the flow. That's why we have a large range of this coefficient. Just by turning this tap, we can change the value of this coefficient from a very small, suppose 0.2, to a very large value. Now when this is, suppose this was the cross section of the pipe opening at this point, when it is only this much closed, then the value is, suppose, 2 or 3 or 5 or so on. But when this is closed by this much, and only through this cross section of the pipe water is allowed, in that case this coefficient will be of a higher value. Then if you close it even further, that is, if this is the cross section and you are only allowing flow through this small area and all the other parts are blocked, so in that case this value of k may go up to, suppose, 200 or 1000 and so on. You can keep on increasing it. Once you completely close it, that value becomes infinity. Once you put infinity here, you're adding different terms, and you're at some point you are using a value of infinity. Now what does it mean? It means that it will not be valid for this kind of a flow problem. And why is that? Because right now when you have increased it to infinity, there is no flow happening at all, and that's how these kind of taps or valves will work. Now there is an interesting thing that you can notice, that when you are when you have, suppose, closed this valve, that means this much is closed and only this much part is opened. But even then, if you have a valve like this and you have some length of pipe available here, or it may be leading to the exit of the tap, suppose. So in that case, once you have only let water flow through this portion and through this entire cross section flow is blocked, then what will happen is, just like use, by blocking using your thumb, velocity through this portion will be very high. And that's why in some cheap plastic taps, suppose, you see that when you close the tap halfway, through this tap water will not flow smoothly and it will flow either through one side or making 2 or 3 streams and so on. That's because as soon as you let water flow through only a small cross section through this valve, that means over this part there is no flow, only through this portion flow is taking place. In that case, the flow will take place like this and there will be some kind of spiraling flow, and the flow will take place, flow will exit this outlet only by the side or by making 2 or 3 irregular streams. But the valves or taps which are very well designed, that means the expensive taps, they have designed the inside of the tap in such a way that even if you close it halfway or uh, 3/4 and so on, then also the inside of the pipe will arrange the flow lines in such a way that at the outlet you will not see what is happening inside, but at the outlet you will still get a smooth stream of flow like this. And if you completely open it, then also you will get a smooth stream of flow, but it will be uh, a thicker flow having higher discharge. But if you half close or only partially open the valve, then it will be a slower rate of flow, but it will be a smooth stream. Now let's take another example that you can practice on your own. So it's an example where we've used some unnecessary bends, so you can keep adding more and more bends and therefore more loss coefficients here, 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 and so on, and then add the frictional losses for this pipe segment, and so on, and again here, here, here. Now let's come to another practical example, that is when you have an overhead tank and suppose this is the shower which is open and some water was flowing through this from this shower, but at the same time somebody has opened this tap. Now water will also flow through this tap. Now will the shower be affected or not, and if affected, how much? That we can also find out. Let's try to approach this problem using a similar approach. But the problem is we have two different head losses. In this pipe or in this shower, the head loss will be the difference between the outlet of the shower and the water level in the tank, which is suppose this level, and so this will be the head loss. In case of this tap, the head loss will be more. So how can we address this problem? That is, let's see. We can now write two equations for these two outlets. For let's call this 1 and this 2. So for 1, the head loss is, suppose let's call it 5 meter, and for this it is, let's say, 3 meter. Then for this setup, the head loss will be given as head loss at this point, head loss at this pipe segment, head loss at this bend, and head loss over this pipe, then head loss at this branch, then head loss at this bend, head loss at the valve, and all along this pipeline, and head loss at the exit. So using those head losses at different points, we can find out we can form an equation for this setup. Then for this setup, we can again form a second equation, which will be again, you'll add head loss at entry through this length, at bend, at this length, and at this length, then this bend, and in between there will be an additional loss at this T joint. T means the letter T because this joint looks like the T letter, therefore some loss will be there, and then this length, this bend, and so on. So now we'll have two equations for two head losses. Now I request you to form these two equations, and so h1 equal to suppose 5 meter and h2 equal to, no, we gave different numbers. H1 equal to, this was given as 1, so therefore yeah, this is 5 meter and this is 3 meter. So now you can find out this. Now you have two equations, and then you can solve for the discharges through this tap and this shower. So this is how we address these kind of problems. I'm leaving this problem to you and to solve, and it will be part of an assignment. I'll give it to you later. Now another topic that I can discuss is that flow through non-circular pipe sections. In general, in most common applications, the pipes that we use are circular, but in some cases there may be non-circular pipes which may be of rectangular cross section or square cross section or hexagonal cross section in some rare cases, or any kind of cross section. So what do we do in this kind of cross sections? The basic principle should be same. That is, the head loss should be a function of the friction factor, then the velocity, then length and diameter, but a rectangular section doesn't have a diameter, and therefore, or a square section doesn't have a diameter, and therefore instead of diameter we are going to use something else which kind of represents diameter. So for that we use something called a hydraulic diameter, and instead of using the diameter of a circular pipe, we are going to use this hydraulic diameter dh. Now how to find this hydraulic diameter? It's actually very simple. You can simply remember this formula. dh is given as 4a by p, where a is the area of cross section of the pipe and p is the wetted perimeter, or in case of pipe flow we can simply call the inner perimeter or simply perimeter. So if we have a square cross section like this, then you will be given the outer suppose the inner length d, inner side length d. In that case, area will be d square and perimeter will be 4d, and we also have a 4 multiplied here, so 4d square by 4d, that's equal to actually d. So in case of square pipes, now we have seen that the length of the side does the same work or represents the um, pipe diameter or the hydraulic diameter. In case of a rectangular pipe, dh is given as 4a by p. It will be 4 into l into b. Let's use small l here, divided by twice l plus b, which is the perimeter, and l into b is the area. So you get the idea that we simply use 4a by p, this formula, to find out some dimension of the pipe relevant to the pipe, which works, which represents the diameter of a circular pipe having similar flow characteristics or similar kind of head loss. Now, if you do the backtracking for a circular pipe, what is the area? Area is pi d square by 4, and the perimeter is pi into d, and we have the hydraulic diameter formula as 4a by p. So in this case, if you cancel all these terms, 4 by 4, pi by pi, and d by d square, it's simply remains d. That means the diameter of the pipe is the hydraulic diameter in case of a circular pipe, and in case of square pipe also, the length of one of the sides is the hydraulic diameter, and in case of a rectangular pipe, it will be whatever you find based on the actual length and breadth. The similar will be the case for triangular or hexagonal and so on. So only thing that you have to remember is this portion, which is hydraulic diameter equal to 4a by p. Now, the losses in pipe flow are characterized, are classified as major loss and minor loss. Now, major loss is the head loss due to friction, which is given by this formula FLV square by 2GD. That is the Darcy-Weisbach formula. But all the other losses, loss at joint, loss at bends, curves, entry, exit, expansion, contraction, or branching, these are called minor losses. Now, one of the problems, you can choose whatever problem you want. Then you can try calculating the head loss or the velocity, and see if you ignore these minor losses, how much difference will it make. We'll see that if the pipe length is very large, that means we are dealing with pipe lengths of hundreds of meters or kilometers. In that case, the minor losses are almost insignificant. But if you have a very short pipe length, in that case, the head loss due to the minor losses will constitute a significant portion of the head loss. We have briefly discussed some of these minor losses and how they come into being, and in the next lecture we will also discuss in detail how each of these minor loss is actually calculated. They cannot be again directly derived using some equation, but generally they are found from experimental data, and therefore those loss coefficients represented by k, those will be found out based on experiments. So we'll see in detail how these minor losses are found and how their coefficients vary and what they actually mean in greater detail in the next lecture. So that's all for this lecture. Thank you.